Welcome everyone to today Innovation Coffee. We're together for another awesome Innovation Coffee. Today is Innovation Coffee and the title is ML on low power Cortex-M with Cartesiam. So I'm really excited for this episode. We have a chance to talk to some of the industry experts actually doing machine learning on really tiny devices. We'll tell you how tiny these devices are in a few minutes. But I'm super excited for this week's episode. But before diving into the episode this week, I wanted to, as usual, hand over to Robert. Hey, Robert.
Hey, Alessandro. Thank you. Yeah. Cheers. Ding. I think I'm going to need to get like a little sound thing. So when we do that, it goes bing. But yeah, thanks, Alessandro. I'm also very excited. Thank you for allowing me the moment here to talk about a little recap. We like to let you know what happened last week. So as you all know, it was Halloween week. It was so exciting. I still have some of my stuff hanging up here, but we got to speak with some of our ARM innovators. We invited them onto the show. We were all dressed up. I was a Viking. Alessandro was a vampire. It seems you found the cure. We had Dara Graylish from 56K Cloud, who joined us as, I think he called himself a spooky monkey, but he seemed to be like a scarecrow. And then Sahaj from 96 Boards, Monaro, who was a floating head. But we talked about spooky tech, the history of Halloween, and Alessandro had a really cool demo. I don't know. Do you want to kind of recap on that demo real quick, Alessandro?
Yeah, it's actually another TinyML demo that I did last week. It's a TinyML demo that was using one of our innovators, actually two of our innovators' technology. So go watch last week's episode for a spooky demo. We actually got it to recognize. It's a computer vision demo that was recognizing different spooky things from Halloween. It was actually fun to do as well. So yeah, go check that out. It was quite interesting.
Yeah, I'm sharing last week's link to the video in the chat right now. I also want to remind everyone that if you aren't already subscribed to the channel, take a second, scroll down there, subscribe to the channel. Like the video, and let's get on with the show. I'm excited. Cartesiam.
Yeah. So let's bring everyone in. We're lucky today. We got 3 guests. So wow. Let's bring in our special guests from Cartesiam. So we've got with us Joel and Francois. So Joel is the CEO of Cartesiam, and Francois is the CTO of Cartesiam. So really glad to have you guys both on today with us. It's amazing. Thank you for coming. Thank you for joining us.
It's a real pleasure to be with you today, or tonight.
Yes, tonight.
It's still day for me.
Yeah.
It's already night for us.
Oh, nice.
Yeah.
Cheers.
Cheers, my friend.
Yeah.
Yeah. True French style. Yes, we like that.
Yeah.
And I also wanted to bring in our other guest today. So we've got a special other guest, Sam Moss. He's one of our engineers and technical experts that do a lot of really cool things. Embedded all-round expert. And thank you. Welcome to the show, Sam.
Thank you very much. I wouldn't go far as to say I'm an expert, but pleasure to be here. Yeah.
So it's going to be an exciting show. I'm really looking forward to. I think we've got 2 demos coming up, right? Yeah, thumbs up. Yeah. So yeah, I'm really looking forward to that. Before we get started with the demos and the tech, I'm really curious as usual. I'd like to know more about your stories and what brought you to this point today, right? So there is this massive TinyML trend. We're seeing a lot of people doing more exciting things on low power devices, and I'm curious to how you got here. Like what made you create a company that actually enables now people to do this. So I mean, should we start with Joel?
Yeah. So first of all, thank you for inviting us to this show. We are very glad to be with you tonight. Well, actually, Cartesiam, we started this journey in 2016, and I should say that prior to that, Francois and I already had a startup that was doing big data analytic on social media, basically. And we realized that even though, let's say, there are a lot of data generated by humans, there are even more data generated by machines. There are 160 billion machines on Earth that are generating a lot of data, and nobody is listening to this data. So we closed the first one, the first company, and we started AppyCube, was the name of the first one, and we started Cartesiam with this idea that there should be a way to analyze all this data on the machines, but not in the cloud, directly on the machine. So we look at the different technology available on the market, and we realize that all the technology have, let's say, they are great AI technology, but they don't fit very well for the IoT environment because they need to require to cloud, they need to have a lot of data, you need to have a data scientist, and so on and so forth. And therefore, we said, well, what if we create a company where we will be able to do not only the inference at the edge, but also the training at the edge. And that was really the let's say the main idea of starting Cartesiam. So we hired PhDs in mathematics, advanced mathematics, machine learning, signal processing, and so on. And we told them, guys, your playground is the microcontroller. So we don't want you to develop another, let's say, a big framework that's working with a lot of memory, a lot of data, a lot of power, and so on. We want you to think inside the box that is the microcontroller. And so the team from Francois, what they did actually is they did not reinvent AI. They really started back from the algebra, and they rewrote from scratch every single machine learning algorithm and signal processing algorithm, so they can work inside a microcontroller, learning and inference. And that took us approximately 2 years to do that, and that's the solution that we have today. So really, the idea was, making AI ready object is very complex. It requires to have two worlds to come together, the data scientist on one side and the embedded developers on the other side. And these two communities, they live separately, they don't know each other, and they don't have much in common. And so we addressed that point, and we said, well, we need to have a solution for this community. And that's why we created our solution, Edge AI Studio, that Francois will present later on, and I guess Sam is going to show some examples as well. That's the short version of the Cartesiam story.
So Joel, I think that this is awesome. The way you summarized it is perfect. It has so many implications here, right? Like when you're talking about putting this AI at the edge, right? Like at the device level, as more and more of these devices, and we're projecting hundreds of billions more, like in just the coming years, all the way up to 1 trillion devices at the edge. There is so much data that is being collected at the edge. And if we just stream all this data back up to the cloud, I mean, it's too much. By putting this out at the edge, not only are we basically kind of doing more analytics at the edge, obviously, but it becomes a much more sustainable solution too, because now we're not consuming all this energy by moving this bandwidth all the way, or all this data through all this bandwidth back and forth just for the analytics. Let's trim it and then send it.
Yeah,
so I love that.
I fully agree with you, Robert. I think the point is, I think the 5G and even the 10G will not be enough to stream all the data. Yeah. This machine today, they are vibrating. They have a temperature. They have an electromagnetic signal. They have many signals. Nobody cares. Nobody is listening to these signals. So one thing we noticed with Francois is that we see a lot of people trying to think like humans instead of thinking like machines. So they think with the sensors of the humans, so with the eyes and with the ears. So they try to have a microphone to listen to a machine, because this is what a human does in a factory. We listen to a machine and say, oh, there is a strange noise on this machine. So they try to replicate. But if you think like a machine, you are going to use the sensors of the machines, like a vibration sensor, electromagnetic sensor, and things like that, to do predictive maintenance, for example. And so if you find a way to capture the data and analyze the data at the very same place without having to go back to the cloud to do all the analysis, it makes a lot of more sense. And in some case, it's mandatory because of the latency, because of the resilience, because of the security issue, because of the power. I mean, so yeah, for all these good reasons, edge is going to be more and more, let's say, present in the industry. But we truly believe that the real game changer is how to make it accessible to a lot of companies so they can implement edge AI without having to capture tons of data, train the data, deal between artificial neural network and k-mean clustering and random forest and things like that, that the embedded developers have absolutely no idea what it means. And they don't know all this world. So they need something simple. Just click a couple of buttons and get a library that will do the job, and that's it. And that's what we are focusing on.
I was actually going to do the same thing that Robert just did. I was going to pull up this comment from my shot JR that really likes your, it's citing what you just said. Your playground is a microcontroller, right? I think that's awesome, right? And
I let you imagine the panic in the engineers team when we say, okay, your playground is the microcontroller. It was like
yeah.
I was actually going to ask you. I mean, we'll dive into more of the details later. But you mentioned that you told, I think 2 years ago. When did you found the company? Was it 2 years ago?
2016.
Oh, so okay, 4 years ago. So you founded a company 4 years ago, and you told a bunch of engineers you got to do machine learning on a microcontroller, right? What was their reaction?
Well, let me tell you a story here, because we have to share the real story here. In 2016, when we launched Cartesiam, we started the company focusing on this. This is Tiny Tile, and it's a neural network on hardware that was created by Intel. So we were, the whole company was working on that. And 6 months after that, Intel said, okay, we are going to withdraw this product from the market. And so we are like, oh shit. So at that point of time, we looked at the market and we said, what is the most pervasive hardware in the planet? And we found that it's the ARM Cortex-M microcontroller. And that's when we made the decision to move to that platform and to say, okay, let's move to ARM Cortex-M, and that is going to be our playground. And we, of course, we hired a bunch of, as I said, PhDs, and we told them, you need to think inside this box. So don't think about unlimited power, and you think inside this box. This is why they had to do all this mathematics to rewrite everything. Because what we didn't want to do is to recreate another framework, another AI framework, because the mathematics is there. It's been invented, I think, in 1954, something like that, by John McCarthy. So the point is not to reinvent, it's to make it work natively inside a Cortex-M microcontroller. And it's true that the Francois team, the mathematicians, they were scratching their head on how to do that. That's why it took us 2 to 3 years to do that, and a couple of patents and things like that.
So we've brought this up, or you two have brought this up on several occasions, and I'm genuinely interested. I took an emphasis on digital signal processing back in school, right? And in the electrical engineering courses that I took, heavily weighted towards mathematics, right? Like you're just basically paper engineering. I'm really curious. You keep bringing up all this math that was done, right? So Francois, could you maybe kind of elaborate a little bit? I know that not everyone might understand what you're gonna go into, but when you refer to all this math that was done, could you give us kind of like a high level view of what you're referring to, like what math was done?
Yes, of course. So the first idea of Cartesiam, like Joel said, was to solve. We are really baby steps in terms of philosophy in the company. So we started with one project, one kind of sensor, one kind of signal. That was the accelerometer. For a project, maybe Joel can show on the camera the device. The device is named Bob. Bob Assistant is a small Cortex-M3 nothing fancy, simple accelerometer inside with a small battery and some kind of LoRaWAN chip. And we went to that company who designed this product, and at that time it was only a shock detector or an orientation detector using the gyroscope. And we said to them, we can upgrade the software, the firmware, and make it a predictive maintenance device based on the same hardware. You don't change the hardware; it doesn't cost you a penny, and we can do it, change it to a predictive maintenance solution. And so we start from there, and we did a lot of hours of testing on the field with industrial companies like Veolia, EDF, French electricity company. And like 1 million hours of data logging testing on the field. And based on this experience, we design the algebra around the problematic, the signal processing around the problematic, saying, okay, we want to be able to do predictive maintenance on every kind of running machines in those type of environments, like pumps, compressor, whatever. And so based on that data, we did it by hand. We designed the algebra around the problematic. And at some point, we designed this product, and it went on the market, and it was a huge success. It's still a huge success in terms of product. And we were thinking, okay, that's interesting. That was a good project for us, but what if we can industrialize that huge task that was finding the good mathematics, finding the good machine learning methods to train on that kind of signal? What are the best signal processing algorithm that can fit those kind of projects? And how can we make it easier, accessible to every kind of engineers? Not only the ones at the office that names the Pokemon team for us, the mathematicians, because they are very rare people. So the idea was to put that inside something that everyone can use easily. So that was the main idea. So in terms of type of signal processing, there are tons of possibilities because it will depend on the kind of signal. If you are dealing with something that is cyclical, if you are dealing with something that is not, if there are frequency involved or not, and etc. So all that search and error is made by the software. We have some kind of search engine that is going to do the try and error for you. That is something you will need to do if you want to design something by hand using whatever kind of framework, of machine learning framework, to prepare the features. And at that point, you will decide what kind of parameters you want to use inside your machine learning frameworks. And all those choices are pretty simple to do if you want to do just a simple demo. I move the accelerometer like this or like that, or I draw some letters. Okay, easy. And you may find a lot of tutorial that can drive you through those kind of example. But when you want to design a product that will go on the field in the real life, and that will support high cost, very expensive machineries, and will be here to monitor 24 hours a day that everything is fine. And if not, it should trigger an alarm saying, okay, there is an issue on the machine, and you should stop the chain and act smartly to prevent something costly. This is not the same kind of project. So this is...
Sorry for pausing you. I didn't want to interrupt, but I wanted to ask you something about, what you were talking about, what Joel mentioned earlier. So, Joel said something interesting, said something about the fact that we have to think like machines, right? So, to your point, depending on what the signal or what the problem is, right, we have to be conscious that the answer might be different, right? But also, it might be different from what we expect the answer might be, right? So the answer might be to actually use some signals that as a human you wouldn't use, right? So effectively, as humans, we tend to use a lot of senses, and obviously we've got some senses that are very strong senses, like vision, for example, right? Where maybe a machine doesn't need to use that because has stronger senses in other fields or in other aspects, right? So what is your approach when it comes to choosing or helping a customer to choose the right signal to use, right? Like, what is the steps that you take or that you suggest someone to take?
So the idea here is to not to start by the signal, by the sensor. Not starting the project, say, oh, we want to use an accelerometer. No, this is not the project. The project is not to use an accelerometer. The project is to monitor some machine, for example. Yeah. So based on that, you can easily test with different type of families of sensor if you have no idea of what is visible or not in the signal, and just do a small data log. You can check the electromagnetic field, for example. You can test the current, and you just check that there is some information, something to check on a simple data log graph. You can see if there is something in this area, and using the same data, you can input that in our studio, in our software, and asking the search engine, is there a solution for me in terms of algorithm using that? And in matter of minutes, the search engine will tell you, okay, yes, I can reach 99%, for example, precision in those kind of signal. So it's very easy to do some testing the first day. For example, you can test 5 different kind of signal, for example. And at the end of the day, okay, the best one is the accelerometer, the best one is the current sensor, whatever. So it's a very pragmatic way to deal with the choice. After that, you can have some. You may have some choices that are based on the price, the cost of the sensor, and the cost in terms of energy. If you want to use a camera, that's great, but most of the time it consumes a lot more in terms of processing, and in terms of the camera by itself consume more than most of the MEMS. So it's very challenging to do a device, for example, that will analyze the vision on battery on something smaller enough. In most of the time, you need a cable. And if there is something I really know, is that nobody wants to put a cable anytime on any project. So if you can run on the battery with a very small footprint in terms of energy, perfect.
Francois, if you saw the back side of my desk and how many cables I have, I go insane just walking around there. Yeah, no one wants cables. I agree. So Francois, I think we've kind of hit Francois and Joel and Sam, we've hit the peak here, I think, of people who are joining the stream. I think it'd be pretty cool to get that demo going because we've hit some key words here. We're talking about, your data studio and all this cool stuff. Can we start? Alessandro, what do you think? Can we move forward with the demo at this point? Thumbs up. Y'all comfortable with that? Excellent. All right. So, Francois, I think you're going to show some stuff first, and then we're going to move on to Sam, right?
Okay.
Yeah, I think it's about time to actually see Cartesiam in action, right?
Enough teasing. Okay.
Yeah, we teased you with some math. Then we teased you with
teasing with math.
Yeah.
Okay, so let me switch to this kind of screen system. So here you have on that part of the screen a small PC fan, and on it there is a Cortex-M microcontroller board from STMicroelectronics with an accelerometer, a very standard one. And by the way, you can find on our website the tutorial that mimic what I'm currently showing you. So on the right side of the screen, you should see my the studio. So the studio, Cartesiam Studio, is a desktop software. And as I already told you, that will help the developer to design the machine learning solution they need for their project. So if I go through the simple steps that are needed to create a machine learning library. So the idea of this demo is to do something to a small device that will monitor, that will learn the behavior of the fan here, based on the vibration, the accelerometer data. And after that training period, it will switch automatically to inference mode. And based on that, it will check that everything is running fine. And if not, it will blink the small LED in red. So currently, the board is in data logging mode. If I show you the demo, show you the Embed Studio here, you should see that the data is flowing through the USB connection. So let me go back to the studio. So when a developer wants to design a library to address a problematic using machine learning, embedded machine learning, the steps are very easy. You create a project here, and you set what kind of target you have. So here, my target is a Nucleo Cortex-M4 board, but you can target any kind of Cortex-M board. We are compatible with all the range of the Cortex-M family. And here you set the maximum amount of RAM you want to dedicate to the machine learning side of your project. And this will be a limit for the search engine. So here I set 16 kilobytes of RAM. And you can choose the type of sensor that is going to provide the data. So you can use an accelerometer, current sensor, magnetic sensor, even generic sensor. If you have something else, a microphone, for example, you can use it like this. So here, in my example, it's an accelerometer 3-axis. So I already create the project. The first step, so here, the first step was global settings, as I showed you. And now we are going to show to the software, to the studio, what kind of environment we want our library, embedded library, to be able to learn, to train on. So for that, we are going to collect some data from the sensor. So it's very easy. You can do it using a log file if you have so, but you can even connect using the USB port and collecting the data directly from the USB here. Okay. Yes, I have to close the port on the Embed Studio. So now I'm collecting some data. And those data are representing a normal behavior of the fan, because as you can see, there is nothing that is blocking or whatever kind of problem on this fan. And you just import that data to the studio. So we don't need a lot of data. It's just to give some context to the software. And you do the same with some abnormal signal, something you want your library to be able to be detected as abnormal behavior based on the library. And here I'm not going to do it, but it's the same. You just collect data. And then you go to the most interesting part of the studio, that is the search engine. So here, the idea, I will start the engine, regular signal. I will limit the quantity of CPU, so my video is continue to work well. And here, the search engine is going to choose between tons of different algorithm mathematic bricks in terms of signal processing, in terms of machine learning, in terms of hyperparameters, to construct, to design a solution for the problematic that I just presented. And there are three parameters that are optimized automatically by the system. The first one is the balance accuracy on that side, so meaning the precision of the library. The second one is the confidence, meaning how confident the library will be about the result of the analysis, the percentage of similarity. And the last one is the RAM needed to run the library. So I set maximum 16 kilobytes of RAM, but as you can see, it already found a solution with less than 4 kilobytes, using less than 4 kilobytes of RAM. So here on that side, you see the three parameters that are progressively optimized by the software. So at that point, the developer has just to go and grab some more coffee and wait for the software to do all the heavy task, to code the library for him and to design it. And after minutes, it will depend of the CPU and the size of the signal, but we should have a pretty good result. As you can see, we have something with 100% balance accuracy, and the confidence is great in the result. So the blue dots are the nominal signal, and the red dot are the abnormal signal. And this is an estimation based on the future library. So now we can test the library we found using the emulator. So here I will use, I don't know, I may use this one. So we just have to initialize the library, initialize the emulator. We can connect using the serial data again. And here we are going to train using 20 lines, for example. So here the data is flowing through the USB port, the serial to the studio, and is learned inside the emulator of the library we found together during the previous step, the search engine. And based on that, we can go to detection and use the second function of the library, that is detect, that will qualify the behavior of the fan based on what has been learned at the previous step. So here at that point, if I put something to create an anomaly on the fan, as you can see on the camera, the library has detected that there is something abnormal happening on this fan. So I'm pretty happy with that library. At that point, I just have to deploy the library inside my device. So I click compile, development version, I download the library, and then I switch to my IDE. Let me change that. Studio, up. So here I'm inside my embed program, embed studio, from one studio to another. And here I just drop the nanoedge.ai.a library and the nanoedge.ai.h file. And now what I can do inside my main program, so I will remove the data logging mode and go libNEI, so the demonstration mode. But here, I don't know if it's visible on screen, but there is two functions that I will use. The first one is nanoedge.ai learn. So directly to that function, I will send my buffer of vibration that I just collected. And I will do that learning training loop 10 times. I don't know if it's 10 times on the parameter, but 10 or 20 times, for example. And I will switch just after that to the detection mode. And I will use the program will use the second function from nanoedge.ai, detect. And every time the function will receive a new buffer from the accelerometer, and we'll use the embedded model that has been created just previously to compare the behavior based on that model and using the machine learning library. And if the similarity is less than the threshold, we should trigger the red LED, or otherwise it's a green LED that will blink. So I just update my device. And should be good. Okay, okay, it's compiling. Flashing. Okay, so now the device, what we can do is remove that cable. And I can bring maybe I can go full screen on the demo. If I do something like this. Sorry for the... So here I can bring my wonderful USB power bank, homemade power bank. So here, the device by itself, without connectivity, without anything else, is training as create a model inside. When the blue LED was blinking, it was the period when the model was training inside the microcontroller. And again, here it's nominal, but if I put something on the fan, it has been detected by the device. Now, if I remove the post-it, it's back to normal. So basically, that's it. We create together a smart device that can detect anomalies on every kind of PC fan. And if I want, I can even do something like use another fan.
It's a different fan.
So again, a new model is created that represents the behavior of that fan. And if I do some anomaly on that fan, it's detected here.
Yeah, that's really the beauty of the system is since the learning is done inside the microcontroller, the library that has been created is a library to learn, in that case, a fan, so a rotating machine. So you can use it on any kind of fan. It will learn the fan at that point. So it means that you don't have to go and collect the data and do a static model that hopefully will represent in the real life what will happen when your microcontroller will hit the real life, or your model will hit the real life. And this is exactly the principle of the first thing we created, or actually Eolan, this company created. It's Bob Assistant. When you put Bob on any machine, it could be an HVAC, it could be a pump or motor, just put it on the machine and that's it. Now it's going to listen to the pump, for example, learn the pump locally, create the model inside the microcontroller, and then switch from learning to inference and start to analyze. If you put it on a different machine, it will learn the other machine, and it will create the model inside the Bob for that machine. So it's very, this is, to me, I'm not a technical person, but to me, I'm a business person. This is extremely powerful for our customers.
Joel, Francois, like I have to say something right now. I am amazed. Okay. So like just hands down amazed. And this is the thing is I just got these headphones. Okay. And I just want to give you an example real quick. Yeah. Cheers. Seriously. Cheers. I'm amazed. I just got these headphones and I was really kind of amazed that I'm able to hit this little button on the back and it listens to my environment and it learns, right? It learns my environment. And now to think that there's these devices out here and that developers can get their hands on these devices and using your technology and the stuff that you guys have developed to simply enable this across the board for anything, right? I mean, I think that this is just so cool. I can already start, I'm going to walk through my house after this call and I'm going to think what I can put these little devices on and then just have it learn. And to see it happen live right now, like you just popped it on a fan and it did it right in front of us in a couple seconds. Like it's so cool. So awesome. Thanks for sharing all that. Yeah.
Thank you.
Yes, use cases are like crazy. There is tons of different possibilities when you think about, okay, now I can train something on site inside a very low cost, very simple device. So then the limit is more about imagination than anything else.
That's the discussion we have with our customers, because the problem is, it's not a problem. The opportunity actually is they all want to move into that space because they heard about artificial intelligence and all that stuff. They don't know how to start. So we bring them the technology, and the only limit after they realize the power of the technology is the creativity of the customers. Because first they are like, oh, wait a minute, artificial intelligence, complex. I don't have data scientists. I don't have data, blah, blah, blah. And then they learn about that, and then they say, oh, maybe we could do this and this and this and that, motor control, and it goes. And then at the end of the presentation, it's like, okay, guys, why we should be focusing only on 1 or 2 projects, right? And then we do the rest. So,
a lot of companies, they're always focused on, let's say, taking an old device and redesigning the entire device to make it smart, right? But I think a lot of this is lost, because then what happens to all the devices that you could then make smart, right? So this is a perfect example. Like right now you have this vibration sensor, but what if I want to like monitor my garage? And I know we're talking about industry versus home, but I can already think of all these smart home applications. What if I want to monitor the light sources in my garage or my washer and dryer machine? What if I want to make my washer and dryer smart and ping things when it's moving and not moving?
With a simple Cortex-M 0 and an accelerometer, in 5 minutes, you can do a leak detector on your flush.
It's amazing.
And let me give you one more example of one of our customers in Japan. These guys, they are doing an air conditioning system. And their problem is to bring predictive maintenance on the air conditioning to know when the filter is clogged, right? So one option was to put a camera, same idea. I have data scientist and I'm going to use a camera to look at the filter. And when the filter is looking a bit dirty, then I have to change it. That's the traditional approach. And we told them, well, guys, what we could do is to have a library inside the Cortex-M of your microcontroller inside the motor control. So we are going to learn the shape of the curve, the shape of the electricity, right? And we will look at this shape. We learn that on site in each of your air conditioning system. And then we are able, when this shape is changing, it means that the filter is clogged. And so without any hardware change, you can do a software update and instantly you have the clogging detection inside your machine. But the reason why they went with our solution is because when they sell their air conditioning across the world, the filters are sometimes, some customers are using a compatible filter that is not exactly compatible because the density is not the same and so on. So if you create a static model, then you get an error because it will say, hey, the filter is clogged while the filter is new. With our model, well, when you change the filter, you learn the new filter that becomes the new reference, and you do the inference based on this new filter. So that's another example of things you could do with this technology.
Love
it's
it.
Very cool. And I'm just going to say, like, I think reiterate what Robert was saying, but it's awesome to see not just this stuff working, but also the fact that now, like, you guys are enabling developers to actually train on real devices, right? And I think this is like, to me, it's super interesting because, as you mentioned, Joe, any device or actually any machine out there is going to have like slightly different, kind of modes or ways of operating, right? So if you can train on or if you could adapt your model to a specific machine, that's super powerful. So you could deploy to all these devices in a factory, for example, and then make sure that each of them is actually capable of detecting the anomalies of that specific machine. Exactly. I think that's super powerful. So yeah, so I'm really excited to see what else is possible with this kind of stuff. And in a moment, we'll actually have Sam show us another idea of what this could be used for. This idea came out of a conversation we had a couple of weeks ago, right, Sam? I think it was.
Yeah. We were on a call just like this, and Joel says, "Hey Sam, there's a guitar over your shoulder there. Why don't you try and do something with the guitar?" So literally, as soon as I put the phone down on that call, I went straight to it and had a go, and yeah, it was great. So I'll show you a demo of that.
Alessandro, before we dive into that demo, can we take the YouTube questions?
Yeah, exactly. I was actually going to pause and take those questions. So a couple of questions. We got one from iShotJR. I'll put it up here. Francois, this is for you. Can you explain how those stats are coming from the board in real time? So you showed some stats on the tool, right? And
yes, I was trying to reply on the chat, but it's a too rich question for my typing speed, so I will try to answer in the video. So if you are talking about the data that is flowing when I'm data logging information, it's only the data from the raw data. And this is very important. We are using the raw data from the MEMS, from the accelerometer in that example. So we are dealing with all the conversion needed to train something. That's done by the search engine. It's part of the bricks we can, the search engine will choose or not. And if it's about the graphic that is showing the progression of the optimization, it's showing the progression of the optimization step by step. It's improving the best library it found in a smart way. It's not a brute force approach. It's more, there is some machine learning involved in the search. So it can be done on a simple CPU, PC CPU, and not on a huge server that you will have to buy on Amazon Web Service, for example, or Azure Sphere or whatever. Azure, not Sphere. Yes.
So they're asking. So Aisha Jar is asking a kind of follow-up question. You can see here, but did you get to choose that? And is that just serial? And then I think he's going on. He's saying, how did you set it up? Choose that, make it send.
It's a very basic setup. It's only connecting your accelerometer in your main program, saying, okay, I want to use that accelerometer. Most of the time there are libraries that are helping you from that are provided by the manufacturer, the accelerometer, the device. And so you fill your buffer of data, and that same buffer, you write it on your serial port in your main program. And on the PC side, you just listen, the software, the studio is going to listen to that port and read, okay, there is a new line of data, new one, and it will be recorded by the studio, and that's it.
All of this is explained in the tutorial, and you shared the link, I think, with the community here. But if you go on our website, Cartesiam.ai, you have a documentation tab and a product tab, and you just click and you have all the, exactly. You have all the details on how to do that and do exactly the demo that Francois did, actually.
Yeah, I just posted also in the chat on behalf of the ARM software developer handle, but go visit Cartesiam.ai. It's a great website too. So, after the show, go check that out. And as we always mention, everything we talk about in this call is going to be provided in the description below. So make sure that, scroll down a little bit if you're watching this right now and check out the description post live. Yeah.
The other question quickly before we move to the next demo is from David W. So he's asking, I think, Francois, you already took that on the chat, but just maybe to share with everyone, could you use this to listen in a car a multi-cylinder engine? And
I really like this example because we were used to use it as an example, saying, okay, at the morning when you start your car, you have some kind of reflex to compare the sound with the usual sound of your car, and you know your car, and it's not the same sound than the other car around. So it's almost the same strategy that we are applying to a microcontroller, saying, okay, this microcontroller is going to learn to train on my engine, my car engine. And if I got two cars, there will be two different kind of model of knowledge, and based on the information from that specific car. So yes, we can imagine something around that.
I would say the answer is yes, but maybe listen doesn't mean you are going to use sound. Maybe you should use vibration or something else. Depends on what you want to do. Happy to have a conversation with you, David.
Okay, you can even use, for example, the pressure at some point, even on the hose or the pipe. I don't know the English term at the exit of the engine, and because the gas is going to flow in a very specific manner when you start your car, or you can even use the current, the voltage of your battery, to check that the way your battery is going down in terms of voltage when you start your engine is an information you can use to check the health of your battery, because when the battery is aging, it will have a different curve in terms of voltage when you start your car. So you can detect that as an information to say, okay, maybe you should change your battery because it's going to let you down in some days, and you want to prevent that. So yes, there are a ton of use cases in a car, more than 2 or 300 microcontrollers in the car currently. So you may imagine that there are tons.
Let's Sam have the demo now.
Yeah, it's time with Sam. Sam's going to show us some more stuff, but I just wanted to introduce, I guess, something that we haven't talked about on the show yet. So there's a lot of TinyML being discussed, and usually people tend to use like Cortex-Ms, but kind of powerful Cortex-Ms. Like Cortex-M7 is a super beefy Cortex-M, right? It's still a low power Cortex-M or microcontroller, but it's super beefy. Actually, we never talked on the show about the ability of doing machine learning on a Cortex-M0 like. It's actually the new version. It's the Cortex-M23. So I'm really keen to have Sam tell us more about what this processor is, what it's capable of, and show us the demo actually. So Sam, it's all you now.
All right, I'll try and make it quick. So like everyone in this stream here, I saw a demo that was quite similar to what I've just seen. And I thought, is it really that easy? Is what they're saying true? Can I just grab a Cortex-M device and program it to do some machine learning that I do not have the skill level to do? And yeah, it really was. So the first thing I did was pretty much grab, I don't know if you can see, almost every different kind of Cortex-M device off the shelf. There's devices here from NXP through to ST, Microchip. And I just made a demo using Cartesiam's libraries and their software, and I managed to get it run on all these Cortex-M devices almost instantly within the same day. So I next wanted to check, can it really run on something as small as an M0, or in my case, an M23? And yeah, I'll show you a demo. Hopefully this will work. Let me try and switch the camera. But I don't know if anyone here on the chat has used an M23 or a Cortex-M0 before, but they are tiny, and I'm talking really small. The Cortex-M23 I'm using has 16 kilobytes of RAM, and it's just an absolutely tiny device. Oh, I think my webcam may have. Let's try that again.
Did you pray to the demo
gods?
I
did not pray to the demo gods. That's my one mistake.
You're back.
Any luck? We all good?
Yeah.
There we go.
Hey, brilliant.
Telecaster.
Yes, indeed. Oh, it seems to have frozen. Okay. Plan B. We are switching to the other webcam. And we'll just angle it.
It was a nice try.
Isn't it, right? Yeah. So let me plug in a power pack here. So I thought, would it be possible on such a small constrained device running at such a low clock speed? I think this device is running at 16 megahertz. And like I said, it's only got 16 kilobytes of RAM. Is it possible to recognize and detect chords on a guitar? So let's have a look. So if I turn the device on, it just flashes orange. Hopefully you can see the colors.
Yeah.
And let's try playing some chords, and you'll notice it will start learning and training, and there's a little LED ring on here. And as I play chords, that ring will just fill up.
E minor.
It's full. The training will be done. So yes, I'm playing E minor in this particular case, but let's just keep strumming away until that wheel is full. Hopefully you can see. It might be a bit too bright. The contrast may be off.
No, we can see it. We can see it. You're good.
Brilliant.
One more to go.
And one more. And boom, it flashes green to indicate the training's done. And let's put it to the test. Let's play an E minor again. We have green. Let's play a different chord. So D, red, A, red again. So that's pretty cool, but you might think that's a bit simple. Can it do anything more complex? So let's try just rebooting again and enter the training phase. Okay, now we'll play multiple chords. Let's try an A, and a D this time. So we'll just keep alternating between them. So this is just to prove it's learning on the fly. It's not hard programmed to detect E minor. I'm just picking new chords each time.
Sam, while you do that, there is a question from the audience. Aishar is asking, what is that pickup or whatever is going on at the end of the strings? What is it?
Just a bridge holder. I can take that off. It just covers my bridge.
So this is measuring vibrations, not sound, right? Because you're clearly you're talking over this, so it's not picking up your voice or our voices or anything. It's just the vibrations.
And there's fireworks going off in the background and music playing and just vibrations. So it's a little
all the pyrotechnics.
Little tiny.
Again, it's very interesting to choose the accelerometer because if you think like a human, you will never choose the accelerometer to check that the chord is the note is playing well. But as a machine, it makes a lot of sense to use the vibration. At the end, the sound is vibration, it's the same. But for human ears, it's not enough. So I really like the idea to use the accelerometer here.
No, exactly. And
did you train it to do 2 different chords now?
Yeah, so we can play, I trained on A and D, so we can try an A. I think I played that a bit too hard. An A and a D. And then let's try a G.
No, that's
red.
G.
And let's go back to that E minor again, just to prove it. Red again.
I love it.
Great.
That's very cool.
That's awesome. I mean,
Shazam of vibrations.
It's true.
That's just absolutely mind blowing. I didn't know what you were going to show exactly. I mean, I knew you were going to do something with a guitar, but I didn't expect you to actually. I mean, it's really cool how quickly it manages to like store the knowledge of what the different chords are, right? Like that was how many tries did you do? Like, was it 10?
I did 12 there, and that was purely just because my LED ring had 12 LEDs. So. But
that's a good one.
Just as a point to say how good it is, I had a harder time lighting the LEDs than I did implementing this whole ML system. So it was that easy.
I agree.
Awesome. Well, I mean, that was just really cool, and I think we've gone through the whole process, right? Like Francois, you showed exactly how to use the tool. Sam, it was interesting because we had this call a couple of weeks ago. And Joel proposed, what about guitar, right? What about doing something with the guitar? And you just did it in no time, right? So, this is the type of thing that I love to show because actually it's not just something, hypothetically cool, but it's actually something that you could do yourself, right? So anyone there that is willing to invest 5 minutes of their time, they could just try this themselves, right? And you've got a couple of different tutorials on your website as well. So I'll share again the link here to the tutorial page. There is a bunch of different tutorials on a bunch of different boards. There's actually a nice one that I really like myself, the coffee machine one. It's usually an Italian coffee machine, so, and it's very in theme with the innovation coffee, right? So
yeah, but soon, I mean, we are going an announcement on the 17th of November. And we'll do a refresh of the website where we are going to put a lot of customer testimonials because, it's cool to see the demo from Sam and so on, but they are real industrial using the solution right now in production across Europe. So, and US and Singapore and Japan and China. I mean, so, it's not only about the cool stuff. It's some people are using that to do real industrial applications in anomaly detection, predictive maintenance, fraud detection, anti-fraud detection, security, and things like that. And we'll feature all of that pretty soon on our website.
So I want to be conscious that we've held our viewers here till the top of the hour. But I also want to express extreme gratitude to you all for joining us. Joel, Francois, Sam, of course, my amazing co-host, Alessandro. We loved it. I mean, Alessandro, we're going to close this out now. Do we give them a shameless plug? Do we have time?
Yeah, I mean, go for it. Joel, Francois, do you want to plug something in at the last minute?
Yes,
I mean,
I don't. The video, the coffee machine video, I made it during the previous confinement when we were locked down just before summer, and I didn't add a lot of things to test in my house, so I decided to transform a classic Italian coffee machine. You know, the coffee pot you put on the gas, and you have to wait the perfect time to stop the gas, because otherwise it would gonna burn the coffee. It's not perfect. So using a simple accelerometer, I transform it in a way that now it prevents that burning phase, even if I'm not just behind, just near the coffee pot. And I let the viewers go and check on our YouTube channel. There is the demo video because I don't have the coffee machine here. And there is a video on our YouTube channel, and you can find the demo.
awesome.
I'll give a little plug for both of you here. Make sure everyone goes and visits Cartesiam.ai, their website. Lots of cool stuff going on there. And if you want to keep up with the stuff that's going on, also at Cartesiam France on their Twitter, go check it out. Again, all of these links, everything we've shared throughout the broadcast will be available in the description below. Over to you.
I just wanted to say also that I've got a special cup here. This is from last year's Hackaday SuperCon. And I just wanted to say that Hackaday SuperCon is actually happening tomorrow. And it's called Remoticon this year because it's actually obviously a remote conference. But actually, the cool thing that I always love every year is the prize, the Hackaday SuperCon prize, that I think is something that anyone interested in technology should have a look at, because it's every year they come up with like crazy ideas, and I was lucky to be the mentor of this prize this year. So I managed to talk to some of the guys and girls working on these projects, and they've done some amazing stuff. So watch it out. It's really interesting. I'm really keen to see who's going to win this prize. So yeah, that was my shameless plug at the end of the stream.
We went together last year, you and me. We went in person
exactly.
to Pasadena. That was a lot of fun. It's an amazing conference.
Yeah, absolutely. So everyone, I just wanted to reiterate that Joel, Francois, Sam, thank you so much for being here with us and spending this time. It was really, really good to have you on and to hear from you directly, what you guys are doing. And excited to, after maybe the next announcements that you just mentioned, maybe we'll have another episode with more details.
With pleasure. Thank you very much.
Thank you, everyone. Thank you, everyone viewing. Have a nice day. Bye.
Bye.
Thank you.
Bye.
Bye.